we can qualify elements inside of networking. And to do that, we have to have some good vocabulary that would help us also with network design. A lot of these are a big deal for network design. So the first one, we've already even seen it, and we'll get more and more involved in network topologies throughout this course. We'll see protocols that help us discover the topology, namely Cisco Discovery Protocol. Topology, strictly speaking, is how we connect up things and how communication flows. That's it. Then we see speed. Hey, we've already seen speeds, haven't we? Gigabit, 10 gigabit, fast Ethernet. So different types of interfaces, different technologies give us different speeds. Now, I don't worry too much about cost of a fast Ethernet port versus a gigabit port, but a 10 gig port, those are pricey. 10 gigabit per second, we don't see that on just everyday computers, do we? And we don't see that on everyday switches nowadays that you would buy from a consumer store, but they are built into most of the chassis that Cisco has for us, 10 gig ports. Those are costly. We also see cost in the wide area network arena as well. When we're connecting up our branch office to our headquarters or any site to the internet, it's going to cost us some money, and that might be proportional to the service level agreements that we get, guaranteeing data rates, availability, uptime, things like that. And availability, I just used a word here that's listed. Raymond, when I say availability, what does that mean?
We're talking about uptime, making sure our devices, our resources, and everything that our users need access to are actually available to them when they need them. And that's very important to our success.
Something that can compromise the availability would be security. Now, Raymond, what kind of security threat would compromise the uptime, the availability of a network device? Is there an attack that could make our network less available?
That would be a denial of service attack. Somebody launching an attack that is preventing our end users from accessing the resources that they actually need to access. So we have to be mindful of the different types of attacks that are out there that it could affect our devices. But that's not the only flavor of attack that is out there. There's many different types of attacks. We have to protect our devices themselves from unauthorized access. We are going to have to make sure we protect our resources that are on our network as well from unauthorized access and modification. So security comes in many different flavors, and we have to be mindful of all those different flavors so that way that we can implement the most appropriate measures for our actual network.
Another characteristic of a network is scalability. Now, this is not the weight that we would get if we put the network on a scale. Scalability has to do with the fact that network designs and the ways that we interconnect and the technologies that we use all have different degrees of growth and support for growth. If I were to use network connections that didn't give me sufficient bandwidth, that could be a scalability issue down the road. But a lot of times scalability goes to the protocols that we use. If I were to use routing information protocol, that's something we run on routers so we can understand where all the different networks are. Well, that's not at all scalable. Whereas if I use OSPF, something we'll talk about in this course, it's highly scalable. The models that we see, have you seen all those models that we have some workgroup switches and then multi-layer switches? Well, that is a model that Cisco has given to us from decades of engineering, analysis, expertise, maturation of understandings of how things should work. And those network models are highly scalable. Now, the one thing that I think is really, really hard here, Raymond, hard to differentiate, is the difference between availability and then reliability. Those two, outside of this course and outside of an IT course, those in many cases are going to be seen as synonymous.
Yeah, because availability and reliability, as you said, they are synonymous. Why? Well, in order for us to have availability, we need reliable components. Think of it this way. I'm available, but am I reliable? That's hard to differentiate here. A lot of people say I'm not a reliable person, but I'm always available to help you. Okay, so let's talk about it from a networking standpoint. I want availability. I want to make sure my resources are accessible all the time. Users can go where they want to go. So therefore, I need switches that I can depend on, that are reliable. I'm going to have to make sure that I have components in those switches that are redundant. Ooh, there's something we haven't even talked about, redundancy. Making sure that if something fails, well, I still have that availability I need. But how do we determine reliability? Well, it depends on how long those different components last inside that actual device. Think about a power supply. Do we know how long a typical power supply lasts for? We might want to look that up. We might want to research a 2960 catalyst switch. How long typically is the mean time before failure? Ooh, mean time before failure. Meaning, how long is it typically going to last, that component, before it actually fails? This will help us determine the actual reliability. And we can do that for a lot of different components and a lot of different devices, so we can plan ahead of time to make sure that we will achieve that availability that we actually need.
There are two ways that we can describe a topology, physical and logical. Well, the physical is how things are connected up. The physical is how things are connected up. And if you haven't seen this before, well, it's good to understand these three core building blocks for topologies. Bus, ring, and star. Let's look at the bus. The bus is something we don't really see too much anymore. What do we see? We see a central conduit. We see lines at the end of that central conduit, which are terminators. Not the robotic terminators, but actually something that has a high resistance that is going to attenuate the signal that occupies this bus. So whenever someone communicates onto a bus, it occupies the whole wire. Everybody sees it. So this is actually shared, because if I communicate, my ones and zeros, my bits that are communicated electrically are going to charge the whole wire. So everyone else has to back off. That's a bus topology. Raymond, how does that differ from a ring topology?
When we look at the physical ring here, folks, notice how we are actually looking at a ring. How are our devices connected together? Well, we can see here that we have one router connected up to another router, connected up to another router, and so on and so forth. So this physical traffic flow now goes around the ring. So that ring topology there, you have to wait for your turn to actually communicate as this token is passed around the actual ring, saying, do you got anything you want to send? Okay, it's your turn now. But this ring topology here, we've got this flow going around. With that bus topology, we had that straight linear flow along that bus with termination points at the end. Here, we're going around and around in a circle. But then, we don't see very many physical ring topologies nowadays either, do we? What do we see? We see the star topology.
The star topology has another name, and we definitely need to know this other name. What does it look like to you? Looks like we got something in the center, then we got spokes going out, right? You hear the word spoke, what do you think? You think spokes might connect up to the hub, like on a bicycle. Well, the star topology is absolutely equivalent to the hub and spoke topology. And this is what we're going to see. When we cable up an Ethernet LAN, Raymond, what sits in the middle of the star topology of an Ethernet LAN?
That would be our actual switch. So we have our switch, and we connect up all those peripheral devices to it. Now, what might be that peripheral device? Well, those are the things that are spokes. What could be a spoke? We could have an end station. We could have a printer. We could have a laptop. We could have a router.
So when we look at a topology, they won't be as simple as this, will they? The bus, the ring, the star. Individually, they're not all that useful. But when we put these together, we can get the complex operation. So you won't see star immediately, but you'll start to eventually be able to squint your eyes and go, oh, that's a star topology in the WAN. That's a star topology in my access layer, because I've got my gigabit ports going up to the distribution layer and my fast Ethernet ports going down to the PCs and maybe some printers that might exist there. And it's good to understand this terminology. There's also a few that we don't see here, Raymond. I don't see full mesh, but that would be where we connect everything together. And I don't see point-to-point. Raymond, what would a point-to-point topology look like?
Point-to-point. When I hear point-to-point, I'm thinking of 2 points and 2 points only. So I have one device, the cable, connecting to another device. Here's our point-to-point topology. We have a direct connection between those 2 different devices. But folks, we have to understand here that just because we're physically cabled in this type of physical topology, it doesn't mean that that's exactly how our traffic is going to flow. Our traffic may flow in a completely different fashion, known as a logical topology. And we can see that here. Look at physically, folks. Physically here, you may not see this, but really what we're dealing with is an extended star. We have a whole bunch of different stars physically attached together. That's what we have. Little hub and spoke here, little hub and spoke there, little hub and spoke there. We attach them all together, the extended star. But how does the traffic actually flow? I want you to focus on our end station labeled A. And our end station labeled A wants to communicate with our server. Now notice, we have a switch that station A is connected to. And then that switch is connected up to another switch. And that server is connected to that switch. Physically, we would think, oh, the traffic should be flowing from A to the first switch, then up to the next switch, then over to the server. But depending on how our network, our switches, our routers are actually configured, the actual logical flow of traffic might be completely different than the physical layout. In this case, look at the traffic flow from A to that server. It goes from A to the switch, to the switch, to the router, back to the switch, and then the server. Now, we don't dive into here why this is actually happening, but we will learn it in this course. But just to give you a clue, our end station labeled A is actually in a different subnet, a different network, than our actual server in this case. So we have to use that router to connect these 2 different subnets, the different networks together. So this might be foreign to you right now, and that's okay. But by the time we get through this course, you'll understand why the logical flow is actually this way in this particular topology.